Hello everybody. In this video we're going to talk about double integrals in polar coordinates. But first let's remind ourselves how everything worked in Cartesian coordinates. All right, so if I wanted to do a double integral, if I wanted to integrate over some region, some function of x and y, and I write dA to represent the area element, all right, so what am I doing? Well, in Cartesian coordinates, I have some region R, right? There's my R, right? Now, what does the dA represent? Well, the dA represents a tiny little piece of area where the width is represented by dx and the height is represented by dy, all right? And because it's an area, I just multiply width times height, and so dA ends up being dx dy, or you could write it dy dx. Now what we want to do is consider how we would set things up in polar coordinates. Now a naive guess at how things would work would be to just replace dx dy with dr d theta, the two polar coordinates. But we'd be wrong if we did it that way. All right, so let's explore things in a little more detail to see how things actually ought to work out. So what I'm going to do is look at the type of region that we'll be dealing with in polar coordinates. So in this case, in polar coordinates, let's think about dr and d theta. Okay, let's think about a small change in r and a small change in theta and see what that gets us. Well, if I look at a small change in theta, we're looking at the difference in two angles, right? So let's look at this angle over here and this angle over here. So we're looking at these two different angles, all right? And we're also going to look at a small change in r. So we're going to start with this radius and go to this radius. Okay, so this will be r1, this will be r2, right? And we have our theta 1 here and our theta 2 here. And so what we end up getting is this wedge shape. Okay, so our delta r is the length in this direction, and the d theta represents the change in the angle in this direction. All right, so this is the region we want to estimate the area of. Okay, so, well, how can we do this? Well, this is a wedge. It comes from circles. If I were to extend these curves all the way around, they would become circles, right? And so this is just a fraction of a circle. So if we think about it that way, I think we can get the area. The circle that corresponds to the outer radius has area pi r2 squared. So to get the area of a wedge like this, if I want to look at the area, and I'm going to call that delta A. So we're going to start by finding the area of this pizza slice here that goes all the way down to the origin. Well, the area of such a wedge is given by 1/2 delta theta times the radius of that pizza slice, r2, okay, squared. And if you think about it, this makes sense. If, you know, for the area of a whole circle, the area of a whole circle is pi r squared. That's what I would get if I plugged 2 pi in for delta theta, because 2 pi is going all the way around the whole circle. If I plug in 2 pi for theta, this becomes pi r2 squared, the area of that larger external circle. Now, I want to exclude this piece, right? So I'll subtract off its area. So I subtract off 1/2 delta theta r1 squared. I can factor out a 1/2 delta theta here, and I'm left with this. So that is a way to compute the area of the wedge shape that we see here. Now, we can do some other things here. What I'm going to do is I'm going to factor this. This is a difference of squares, and so it factors as follows. Okay, now let's look at some of these things. R2 plus R1 over 2. If I pull that out, that's exactly the median, the middle between R1 and R2. All right, so let's just call that r, okay? So I'm going to call that middle radius r, and I see that 1/2 times this makes r. So I really just have r times delta theta here. And then what's r2 minus r1? Well, that is exactly delta r. So we see that the area of this wedge is r times delta theta times delta r. Now, remember how when we integrate, the deltas become d's, right? Just like if this was an actual finite piece here, I would have delta x and delta y, and only after we take the limit do they become dx and dy. Well, when we take the limit here, what we're going to get is dA, right? So that's the same area element idea that we had here, but we see here what this is going to become is r, and I'm going to rearrange terms a little bit. It's going to be r times dr times d theta. And so this is how we find the area element in polar coordinates. So it's not as simple as just taking dr times d theta. We have to factor in this r here. And that should make sense to you when you actually look at the picture, because for a fixed delta r and delta theta, you know, if I took the same delta r but farther out, you see we get a much bigger wedge, right? It's a much larger area, even though I have the same delta r and the same delta theta. So it should depend more on just delta r and delta theta. It should also depend on how far we are out. The farther we move out, the bigger these wedges get. And that's what this r term is telling us. All right, so let's apply this to a particular problem. We want to compute this integral over the region R, where R is the disk of radius 1 centered at the origin. Let's just go ahead and draw a picture of that region just to make sure we understand what we're doing. Disk of radius 1, so it's just the unit disk. And so we're just integrating over this region. That's my R. All right, well, what we're going to do is set this up in polar coordinates. Now remember, we had some formulas to convert from Cartesian to polar coordinates. We knew that r squared was equal to x squared plus y squared, and tan theta was equal to y over x. These are the formula that we had to convert. Well, if you look at this, this is just 1 minus r squared. Right? So I can convert this integral into this integral. Okay, good. Now remember what we said a little while ago. We said that dA is the same as r dr d theta. So let's make that substitution. Okay, now how am I doing this? I set it up dr d theta. I could have done d theta dr, but I set it up dr d theta so we can determine the bounds here. So let's look at our picture. What are the bounds for r? Well, r, we're filling in this entire disk, so r goes from the center all the way out to the perimeter. We said it's a unit disk, so we go from 0 to 1. So when I write out the bounds here, I know r is going from 0 to 1. Now, what about the d theta part? Well, we start with from theta equals 0, and we go all the way around the entire circle. So that means theta goes from 0 to 2 pi. You alternatively could have gone from minus pi over 2 to 3 pi over 2, or from pi over 2 to 5 pi over 2. Any of those setups will give us an equivalent answer, but I think the most basic way to do it, it's always good to use zeros when you can, right? Go from 0 to 2 pi, that'll work out great. So this is the integral we have to do. So now it's just resolving this integral. So let's go ahead and do that. So I integrate the inside with respect to r. I think the easiest thing to do would be to distribute first. So there we go, antiderivatives. And I'm going to evaluate this quantity from 0 to 1, as I said. Okay, when I plug in 1 for r, Well, I'm just going to get 1/2 minus 1/4. When I plug in 0 for r, I get 0. So 1/2 minus 1/4 is the answer. That's 1/4. Okay, so now we're just doing this integral, and I think you can see from single variable calculus that's pretty easy to do. That's just going to be 1/4 times 2 pi, or in other words, pi over 2. And that's the value of our area integral. All right, in our next problem, we're going to be doing this integral, the double integral over a region R of 3x dA, where the region is given as follows. Now, it looks like everything's set up in terms of Cartesian coordinates, but it turns out this is a good problem for polar coordinates. And the reason is I'm seeing this right here, x squared plus y squared. That reminds me of r squared. That's what that equals. So this is just saying that r squared is between 1 and 4. In other words, r is between 1 and 2. So let's draw this picture. Well, r goes from 1 to 2. So 1 to 2. Now we're saying that x is positive. So theta is going to range along all the values that keep x positive. So theta will come down here for minus pi over 2 and go all the way up here to positive pi over 2. But it won't go over into this region because x needs to be positive. So if we just sketch all those points that have a radius between 1 and 2 and those values of theta, what we see is we get this sideways rainbow shape. This is r. And now I see, just by looking at this, it's clear polar coordinates are the way to go. You could do Cartesian coordinates, but it'll be a lot messier. So polar coordinates will make this problem quite a bit easier. And I can see that just because this is a very circular looking region, right? So let's set up this integral. So this double integral, well, let's see. What is x? Well, remember that when we relate polar and Cartesian coordinates, we had these equations. We had x equals r cosine theta and y equals r sine theta, right? So I can replace x with r cosine theta. So that's what I'm going to do. So this integral is the same as this integral. Now, dA I can express as r dr d theta. And don't forget this r. That was a very important element of this whole thing. Okay, so now what were we doing? We said r was going from 1 to 2, right? So in my inner integral for the dr part, I'm going to go from 1 to 2 here. And theta, let's look at that. Theta is actually going from minus pi over 2 up to pi over 2. So those are the bounds I'm going to put on this integral. And actually, I'm going to take this r and multiply by that r. Let's make this 3r squared. Okay, so let's do this inner integral, integrating this with respect to r, treating theta as a constant. And I'm going to evaluate that from 1 to 2. Okay, so if I plug in 2, I get 8. If I plug in 1, I get 1. I take the difference, I get 7. So I'm going to end up with 7 cosine theta. Okay, take the antiderivative and evaluate it from minus pi over 2 to pi over 2. Well, sine of pi over 2 is 1. Sine of negative pi over 2 is negative 1. 1 minus negative 1 is 2. So we just get 2 times 7, that's 14. All right, for our final problem, we will find the area of a single petal of the flower shape described by r equals sine 3 theta. Flower shape. What are they talking about? Well, let's try to graph this and see what they're saying here. Okay, so let's see. Let's start when theta equals 0. When theta equals 0, it's sine of 0, that's 0, so r is 0. So we're going to start at the origin. Okay? Now, when theta increases, well, then sine increases, so r is going to increase. So as I move away, as I increase theta, I'm going to be moving away from the origin. Now, by the time theta gets to pi over 6, then 3 theta will be pi over 2. Sine of pi over 2 is 1, and that's the biggest this is going to get. So when we're at pi over 6, this will become 1. So this thing, looks like I already messed it up a little bit. Let's see. But pi over 6 is actually like over here. So it looks like it's going to come out this way. And it'll have, this is distance 1. Okay? Now it's going to start getting smaller after that, right? Because after, when theta gets bigger than pi over 6, this will be greater than pi over 2 in here. And that's when sine starts to decrease. So it's going to start coming back down. Okay? By the time this gets to pi over 3, we'll be taking sine of pi. Sine of pi is 0. So it's going to come, by the time we get to pi over 3, this thing will come back over here. Now, as theta goes past pi over 3 and starts spinning towards pi over 2, that's when we're pointing vertically here. Well, this is now swung us back here. We're actually going into the negatives. So r is going to be negative. By the time we get to pi over 2, we're going to have 3 times pi over 2 is 3 pi over 2. Sine of 3 pi over 2 is negative 1. So as we approach pi over 2, r will be negative and will swing down this way. And then when you go past pi over 2, we go past 3 pi over 2 in here, right? Well, that's where sine starts to increase again, higher than negative 1. So now we're coming back to the origin. And if you keep going with this logic, you'll see this thing spins out this way and comes back like this, and it will loop around and around and around this flower shape. So what we're looking for is the area of one petal. So we're just trying to find the area of this region right here. Okay, so what we want to do is we want to look at this double integral. Now we want to find the area. How do you find the area of a region? Well, you just integrate the function 1 over the region. Because all you're left with is dA. And when you integrate dA, you get area. All right, so if you ever want to find the area of something, just integrate the function 1. Now, remember polar coordinates says we can express this as r dr d theta. All right, cool. Now I wrote dr d theta, not d theta dr, although I could have written d theta dr, but I wrote dr d theta. So the inner integral is going to be our bounds in terms of r, and our outer integral is going to be the bounds in terms of theta. So let's see what we get here. The bounds in terms of r. Well, r is going to go from 0. If I pick a theta, I'm going to let r go from 0 out until I hit the edge of the petal. Okay, so I'm going to start at 0, and I'm going to go out till I hit the edge of the petal. Well, what defines the edge of the petal? Well, that's what this equation was doing, right? When r equals sine 3 theta, we are on the perimeter of the petal. So I'm going to go from 0 to sine 3 theta. Now, theta is going to go from, well, we said that to get from here back to here, it's when theta went from 0 to pi over 3. Okay, so this is the integral that we're doing. And when I look at this, I'm thinking actually it would have been hard to set this up d theta dr, because we would have had to invert this equation and solve for r in terms of theta to get our bounds on the inner integral. So actually I wouldn't recommend doing that. Okay, so we're going to anti-differentiate this. It's 1/2 r squared. And we're going to evaluate that from 0 to sine 3 theta. All right. So let's see what we get here. And then we're going to evaluate this as 0 and subtract it. But this, when you evaluate it as 0, you get nothing. So that's that. Okay, so now we just have to integrate this. This is a single variable calculus problem. how do we find the antiderivative? Well, the trick here is whenever you see a sine squared, we can think of using a half angle formula, because we know the half angle formula for sine says that sine squared of something is given by 1 minus cosine of twice that thing, so it'll be 6 theta divided by 2. All right, so proceeding along here, okay, I got 1/2, 1/2. I'll just pull that 1/4 out of the integral. And what do we have left on the inside? 1 minus cosine 6 theta. All right, so these are not too hard to antidifferentiate. And I'll evaluate this from 0 to pi over 3. Okay, well, if I plug pi over 3 in here, this becomes pi over 3, right? Then I get sine of blah, 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 blah. Okay, so, well, pi over 3 times 6 is 2 pi. Sine of 2 pi is 0. So this whole thing is 0. And when I plug 0 in here, I get 0 minus, well, sine of 0 is 0, so it's gone. So the only thing I get is just when theta equals pi over 3. And so we have 1/4 times pi over 3, and that is, of course, pi over 12.